a new topic, role of data structures in algorithms. But I want to complete one last topic from our B.4. B.4, so we finish that polynomial evaluation part. But still, the last one, B.4, visualize performance improvement. Because remember, this week, I need to give you the first programming project this week. After Thursday's class, I will give you the first programming project. I will explain the main idea in the project. Yeah. Cool. Okay. Yeah. All right. So visualize. We know our Horner's rule is much better than the brute force method. Well, how much better? Do you have an idea? Nobody has a clear idea how much better it is. Here, I try to use a concrete way to show you how big is the difference. In our programming project number 1, you need to write a program to compare how much is the difference. Okay, all right. Here, so visualization, I try to find a way to let you see the difference. Here, remember the Horner's rule, the biggest change is we reduce the multiplication quite a lot. How much? From this many, 1/2 times n plus 1, from that number, that expression to n. We know it's a big improvement. But do you have a clear idea how big is this improvement? That's the question. We want to see that one. Okay, yeah. All right. So, how to visualize it? We want to see something better. Okay, we want to see some concrete numbers so that we can feel the huge difference. All right, let's work on some examples. Let us do some experiments here. What kind of the first experiment? We assume n equals 1,000. How about that? 1,000. It's a pretty big number. Usually, when you evaluate a polynomial, you never have this large polynomial degree, right? 1,000 degree. Okay, so you have quadratic, you have cubic. You don't have this large number. Yeah, but for us, we do our computing problem here. We put ourselves in a situation we are in a big data era. So our data amount could be huge. Okay, so you need to prepare yourself to handle the data size this large. Okay, n equals 1,000. So let's plug in these two expressions. Left-hand side, right-hand side, yep, and 1,000. Left-hand side, plug in, and we just do approximation. Okay, not necessarily exact number. Yeah. All right. So that here you can see approximately 500,000. 500,000. That means using the brute force method, you need to do 500,000 multiplications. But if you use the Horner's rule, you only need 1,000 multiplications. That difference. Okay. The ratio 500 to 1 ratio. Is that big? 500 to 1 ratio. That's an improvement. You use 500th amount of time, you can find the answer. Is that big improvement? 500th of the old response time, you can find the answer. Is that much better solution? Okay, yeah. This is our first experiment. Now I want to do the second experiment. This time, we take n 1 minute. 1 minute. That large polynomial. Okay? Yeah. All right. This time, let's plug in what's the ratio difference, and just 1 minute. Oh, you already feel pretty big. For the left-hand side, after you plug in 1 million and how large is this number? How large is this number? Can you tell me what is this number?
500 billion? No, yeah, 500 billion.
Yes, 500 billion. Okay, yeah. Less than 1 trillion, 1/2 of the trillion. Yeah. But we want to take the ratio. What's the ratio? How large is the ratio? 500,000 ratio. 500,000 to 1 ratio this time. That's the difference of these two methods. You can see where n becomes larger and larger, the difference is also bigger and bigger. See? Yeah. So here, you have any impression in your mind, or you can imagine in your mind how much is this big, this difference, 500,000 to 1 ratio. It's still hard, right? You know, that number is big, but still, it's hard in your mind. How much is the difference? Here, let me use another way to let you feel about this big difference. All right, let's use the concrete time, because we have feeling about time, right? Time period, how long? You know, 1 hour, 1 day, how long is that? We have that kind of feeling, right? Yeah. So here, let's use time unit 1 second. That 1, 500,000 to 1, that 1 corresponds to 1 second. How about that? 1 second. Convenient, then 1 second. So now, with this ratio, we apply Horner's rule, we use 1 second. We can find the answer, 1 second. Okay. You hit the enter, after 1 second, you see the answer. All right. Then the brute force method, the old one, you hit the enter key after 500,000 seconds. You see the answer. 500,000 seconds. How long is that? 500,000 seconds. The, oh,
538 hours.
good, good. Yeah. Hours. All right, that's hours. Now I like to convert it to number of days. 5.8 days. 5.8 days. See? Now you can feel the huge difference, right? Yeah. To do the same thing, you evaluate the same polynomial on using 2 different algorithms. The brute force algorithms and the Horner's rule algorithms. One, you only need 1 second. The other one, you need 5.8 days. Near 6 days. Think about that. Okay? Yeah. Think about in the real world situation. Suppose you provide business solution to your customers. Okay? Yeah. If you have a very good algorithm, very fast, to get a computation result in 1 second, so you will be very happy to bring it to your customers. Show them. I can find your solution just in 1 second. So your customer will be very happy. For the other one, the same solution, it's correct. It's not wrong. But it's too slow. Think about it. If you bring that bad solution, you need your customers wait 5.8 days. Even if it is correct, it's very likely your customers won't accept it. So now you feel, so for this algorithm, our goal, or one of our goals, we want to get the fastest possible algorithm, just like the second one, on this rule. And it's possible, you can see the first one, the brute force one, if you do not know the Holmes rule, then 99% of the people will just take the brute force method, right? Without any problem. Brute force method. Okay. But you can see in that big data processing, that could be very long period of time. So now you can imagine how important for the algorithm improvement. All right, so this is just our first example. Later, we have many situations we will have similar improvements. All right, so that's the B.4, the first topic. Second, all right, yeah. So here, second topic, part C. C.1, search unordered arrays. So let's do our second computing problem. This one also very easy. Problem number 2, search an unordered array. Give you the problem. Given an unordered array, we use a pair of brackets, indexes from 0 through n-1, n elements, and a search key k. K, also given. The goal, we want to find index I such that k equals 8 of I. That's simple. So it's a basic, simple question, but we have something useful to learn. Okay, yeah. Let me give you here the problem type. That's the search problem. Basic. So for this class, we will learn 3 different types of basic computing problems: search, sort, and selection. 3 different types. Here, the first basic type, search type. Data structure used in this example, array. Okay, array. All right. So the reference in the textbook, I also put it here, section 2.1. Yeah. All right. So to solve this problem, actually it's pretty easy. Yeah. So everyone here, I believe you can solve it easily. But when we learn this example, there is something important we need to learn. Why the data structures are important in algorithm design. For this one, we may not be able to see the big difference. But when we need to solve some relatively hard problems, then the data structure could be very important. Because this problem is too simple. Yeah, so we just use the simplest data structure array, simplest, unordered array data structure. So we can solve it easily. All right. In general, yeah, so let's look at this question in general. Through data structures, we can make our data well organized, especially when we use advanced data structures. So we can organize our data in a very special way. So then we can take advantage of the special structures and we can have faster performance. In our module 5, actually, very late in this class, module 5, I will show you, we will use advanced data structures to get a solution with some good problems. Here, for the analysis, for the stable measure of efficiency, performance efficiency, stable measure. Remember last time we talked about the stable measure. Here we use another concept. It's called a basic operation concept. Basic operation. How do we measure the efficiency? We use the number of basic operations. So what's the meaning? Basic operation. Here, the meaning of the basic operation. So which operation dominates your algorithm? So you use the most in your algorithm. Yeah. The previous our problem number 1, multiplication is the basic operation because we use multiplication the most. Okay. So for this question, comparison is the basic operation. We do comparison the most, okay? The dominant operation. Yeah. So we compare K and A of I, same or not same. Okay? Yeah. So we start with initial position I equals 0. All right. If K equals A of I and K not equal A of I, we only have these two cases. If K equals A of I, we're done because we find the answer index I. If K not equal to A of I, we don't care. It's greater, smaller, that's not important. We only want to know they're different. Then we move to the next element in the array for another round comparison. Okay, yeah. So that's the details of this algorithm. All right. Yeah. But you may have the situation after you compare all the elements in the array, you cannot find any element whose value equals K. That's possible. If that happens, the search fails. The search fails, yeah, and yeah, usually your function returns negative because negative, it's not a valid index number. Not a valid index number. So when you see the value is negative, you know you couldn't find the search key in the given array. Yeah. But you have the answer. All right. So this algorithm, this simple algorithm, we call it sequential search or linear search. Some people call linear search, some people call sequential search. Okay, yeah. All right. So that's so simple. Yeah. But now we need to move to the analysis part. Analysis. We want to know how fast. So we want to get an idea how fast is this algorithm. We want to use appropriate measure to see its efficiency. So next, let's do the analysis on its efficiency. Okay? Because we want to use a stable measure, here we need to count the number of comparisons. How many comparisons do we need? There are many different cases. So here, let's do a chart to see for all those different cases, what's the comparison of? So the number of ops, the second row, if k equals the first element, a of 0, you only need one comparison. Then you'll find the answer. Your function terminates after one comparison. Okay? If k equals a of 1, second comparisons, and so on. Okay? Yeah. If k equals the last element, n comparisons, no match, you couldn't find the search key in the given array, there is no match. Also, n comparisons. So that's all the possible cases. No. From this chart, you can see the best case. One comparison, we call it the best case. If you are very lucky, you get the best case. So here we have this best case efficiency concept. Then the worst case concept. The last two cases correspond to the worst case. N comparisons. Two cases, not one case, two cases. One, you have a match. After n comparisons, you have a match. The second case, no match. After n comparisons, no match. Two cases for the worst case. All right. Now, the most important point I want to convey in this example. Now, we have different cases. Question is, I ask you to give me the description of the overall efficiency. What do you think? The best way to describe the overall efficiency. Overall.
Inefficient, probably. Inefficient because it's like,
Yeah, let me just ask you. Do you think if I use best case to describe overall efficiency, is it good one? Best case to describe overall efficiency.
That's
Not good, right? If I use the worst case to describe overall efficiency, do you think it's good? Worst case. Still not good, right? Because it's not that bad, right? Which one you feel the best way to describe overall efficiency? Yeah, something in the middle. But do you have some better way to describe it? Yeah, it's correct. Something in the middle. Yeah.
intermediate,
Intermediate. Yeah.
average.
Good. That's the best word. Average. So we call it average case efficiency. Average case efficiency. But the question is, something in the middle, your description is too rough, right? We need an accurate. We need some accurate way to calculate average case efficiency. That's the most important point in this topic. I want to talk about how to calculate average case efficiency in this example. We have n+1 cases, right? Hold on. We have n+1 cases. How do you calculate the average case efficiency? What is the most accurate way to calculate the average case efficiency? Do you have any idea? Yeah. How can you make some fair way? Yeah. We want some fair way to do the calculation. Yeah. Not the biased way, right? Biased way, you favor the best case side or you favor the worst case side. For the average case. So let's see. All right. How do you take the average? When you take the average, do you know there are many different ways to take average of given set of numbers? Mean, right? Another way to say the average, mean, find the mean, right? Mean value. But for the mean, do you know there are many different means definition? Arithmetic mean, geometric mean, harmonic mean, right? There are many different ways to define the means. Here, we want to use the best way to calculate the average. The mean, the average. All right. So how to take average of these n+1 cases in a fair way? That's what we need to do. To do it in a fair way, we need to make some assumptions. Otherwise, you may not give a fair average calculation assumption. That means there is some important information missing here. So what information is missing here? Let's move to C.2, average case efficiency.
Average case efficiency calculation. Yeah. But we need to make some important assumption, or there is an important piece of information should be provided someone, yeah. Or we need to find it. Yeah. So what that information? So that information, think about. Given a search key, that could be in the array or not in the array, right? Yeah. So that's two cases, the search key given in the array or not in the array. But do you know in what percentage of time it is in the array? What percentage of the time it's not in the array? Yes, that information is missing because 100% in the array, that's one possibility, right? 0 possibility in the array, also it's possible, right? 50% of the probability in the array, also possible, right? Yeah, that means we need to have the probability number given. Yeah. So for these cases we have here, assume, yeah. So yeah, in these cases, yeah. If we consider these cases, for the first n cases, we can assume they have the same probability, right? Yeah. Case 1, case 2, case 3. Yeah. So we can assume they have the same probability. But for the last case, no match case, the last one. The probability for the index case. Yeah, index case, that means the match case, right? Your function returns a valid index. That's the index case, okay? What do you mean, the index case? It means the function returns a valid index. Okay, yeah. The -1 case, it's not a valid index. Okay, that's the no match case. Yeah. So we need to know the probabilities for these two cases. Yeah. Yeah. The match case, let's assume the probability for the match case is P. That P is a number between 0 and 1, inclusive. Could be 0, could be 1, yeah, between 0 and 1, P. Yeah. But that number should be given before you calculate the average case efficiency. Okay, yeah. Then, no match case, 1 minus P. The probability, you know that, right? Yeah, because the complementary case, right? Yeah. 1 minus P, the probability. After this information, P given, this time, do you know how to calculate the average case efficiency? This time. Because now we have all the information we need. Can you find a good way, appropriate way to calculate the average of all these n+1 cases this time? You have the probability number. Yeah, probability number. How to do the calculation. Yeah. So this time, we be careful. So we need to put all n-1 cases together, but each case, how to look at the contribution from each case. Contribution in the number of comparisons. Think about it. Case 1, one number of comparison, but with its own probability number. Case 2, two number of comparisons, contribution, but it has its own probability number. Think about that. Each case, there is a corresponding probability number. All right. First subcase. The match case, we treat it as the first subcase. We have two subcases. Match case, no match case. Two subcases. For the first subcase and the second subcase. For the first subcase, because we assume these n cases, they have the equal probability, right? Equal probability. Then, when we take the average, we just do the ordinary average. Now, we add all the numbers up, then divided by the total number of cases, n. So its average is 1/2 times n+1. That's for the first subcase. First subcase. Second subcase, only one. Only one case. Second subcase. N comparisons. So we just take the n for the second subcase. Now, we want to put these numbers together. one here, one there. Yeah. Two different sub-average numbers. Yeah. We treat them as sub-average numbers, subtotal, okay? Sub-average numbers. But we want to combine these two sub-average numbers in an appropriate way. And we know the first subcase, its corresponding probability is P. Second subcase, its corresponding probability is 1 minus P. Now you tell me, what is the best way to put these two subcases together in a fair way? Because if the probability number is larger, then the contribution is larger, right? That's subcase. Contribution is larger. If the probability is smaller, then the contribution of that subcase is also smaller. Okay? So here we do a kind of average. You may have heard of it. It's called a weighted average. Have you heard of weighted average? That's another way to do the average, but it's a weighted average. Each subcase, there is a weight associated with it. When we do average, we need to assign an appropriate weight for each subcase. That's the weighted average. What's the weight to be used here? Probability. Right? But we use the probability as the weight to do the weighted average. All right? Yeah. So the weighted average formula, yeah, look at the weighted average formula here. Yeah. The average of the first subcase, 1/2 times n plus 1, multiplies its weight, its corresponding weight P, probability, plus the second subcase average, just the n, but we need to multiply its corresponding probability for the weight, 1 minus P. So this time we get a weighted average. That's the best one. So this is the best way to measure the average case efficiency. And if we use this number to measure the overall efficiency, then it's the best. Think about that. If we use this one, this expression, to measure the overall efficiency, that's the best way. Yeah. Because we consider all the possible cases and we put them together in a fair way. Yeah. Because we consider the probabilities. Yeah. For each case, if the probability is large, the contribution also is larger. Yeah. Yeah. So that's why we say it's a fair way. Okay. Yeah. All right. Yeah. So in this class, when later we need to calculate average case efficiency many times. Yeah. Every time when you need to do the calculation, you need to use this idea. Yeah. We describe it here. Yeah. All right. Okay. Yeah. And before I move to the next topic, let me say something. To get things right, because when I ask you questions, sometimes you may use different formulas. So here, this formula given here, that's the exact formula, okay? Exact formula. That means no error. It's precise, it's accurate, no error. Yeah. So some of the formulas are the exact formulas we used in this class. But in some cases, we use approximate formulas, not exact. Approximation. That's also very common. We use approximation. Yeah. So here, we may have approximate formula. Yeah. Because when we do the approximate formula, we can ignore some minor terms to simplify the original formula. Here, that, for example, that +1, we can ignore the +1, so we can get approximate formula. Yeah. So here, this approximate formula, we call it, it's the dominant term in the original formula. Dominant term. Yeah, because this term represents the biggest share in the original formula. The remaining part is very small. We can ignore, yeah. But this one is approximate formula. Approximate formula. Yeah, not exact, okay? Yeah. Okay, approximate formula. Yeah. But you may ask, when we use approximate formula, when we use exact formula? Yeah. Usually when n is relatively small, we use exact formula. When n is very large, we use approximate formula. When n is large, so that small difference is not important, right? Yeah. So we use approximate formula. Yeah. Yeah. So probably, yeah, approximate formula. All right. Yeah. It's 2p or 1p. I'm not sure. 1p or 2p approximate. Yeah. Anyway, yeah. All right. Yeah. So we finished this topic. Yeah. Yeah. But in my questions, sometimes you use exact formula, sometimes use approximate formula. Okay. So you need to make sure. If you feel not quite sure, you can ask me. Okay. You can ask me. So I will tell you. Yeah. Exact formula. Yeah. But first, you apply this guideline. When n is relatively small, use exact formula. When n is very large, we use approximate formula. Okay. Yeah. All right. Yeah. So we finish this topic. Yeah. Then the next topic. Remember, in our quiz 1. Yeah. Have you tried the quiz 1 questions? Quiz 1. Okay. Yeah. Some of you may try it. Yeah. So nobody asked me that questions. Quiz 1. Yeah. Here. Yeah. I mean, I take a look, and because this topic relates to one of the questions in quiz 1. So I want to point to that question first. Yeah. Here, oh, you can see it. Oh, good. All right. You can see it. Yeah. Question number 10. Think about it. Question number 10. Yeah. Is it possible that the Horner's rule may not give you the best solution to evaluate certain polynomials? Think about this question. Is it possible? We only consider special cases, not a general case. Can you imagine some special cases? In those special cases, the Horner's rule may not give you the best solution to evaluate those polynomials. That means you can find better solutions than Horner's rule solution. Is it possible? So think about that. Okay? Yeah. So that's the question number 10 in this first quiz. Okay, yeah. Here, this topic, C.3, I will show you some interesting things that would be very helpful for that quiz number 10. Okay, yeah. So let me go to this topic. All right. Here. All right. All right. How to evaluate the monomials efficiently. Monomials. Yeah. So I mentioned this term in part of B. Monomials, we mean x to the kth power. Okay, that's the monomial. Okay, x to the kth power, monomial. Okay, so here the question: if we want to calculate, find the value of a monomial given x and k, we want to calculate x to the power of k, this number. Do you have some better idea to use fewer number of multiplications to do it? Find the monomials. Okay, yeah. So the goal, we want to find x to the k. Okay, yeah. Find x to the kth power with the minimum multiplications. That's the goal. Okay, that's the goal. Yeah. All right. So here, yeah, because we do not have much time, so let me go a little fast. Here, the main idea. Okay. In order to do this kind of computation efficiently, so here I give you the general way to save resource. Yeah. Computation, we treat computation as our resource. So we want to save our computation resource. One way to save our computation resource, we want to reuse our resource. Here, the idea is reuse your resource as much as you can. That's the general idea, okay? Reuse your resource as much as you can. Okay, so that's the general idea. But how, right? You want to know how, okay? Here I show you how, then you can apply this similar way, you know, in many different cases. Yeah. Yeah. So let's see the example. For k equals 4. So let's look at this special case. Now we want to calculate x to the 4th. Yeah. As fast as we can. Okay? Yeah. All right. Or save our resource. Yeah. The first step, step 1, we calculate x times x. One multiplication, we get x squared. X squared. Yep. So the first step, first multiplication, x squared. All right. Yep. Now we need to reuse our computation results. Reuse our computation results. Okay? Because you already have some computation results. That's valuable, right? You get this computation result using your precious resource. So you want to reuse as much as you can. Okay, yeah. So here we want to reuse our computation results. Okay, yeah. So step 2, because we already have x squared, right? X squared times x squared. When we do our second multiplication, we know these two numbers, x squared numbers, we just multiply it with itself. So we get x to the 4th. That's what we need, right? X to the 4th, that's our goal. Find x to the 4th. So here you can see we need 2 multiplications. For x to the 4th. Is it better than Horner's rule?
Yes, I have a question. Wouldn't this used to be multiplication? You didn't know what? Never mind, you're right.
So we jump faster. So we do not do that x squared times x to get x cubed. Then x cubed times another x to get x to the 4th. That's our old way, right? Here we jump a little faster, x squared times x squared. So now you look at the title of this topic called repeated squaring. Here we do squaring operation repeatedly. Okay, yeah. So the next one, for k equals 8. So this time to calculate x to the 8, how many comparisons? X times x, we get x squared. That's 1 comparison. Okay, yeah. X squared times x squared, our second multiplications, x to the 4th. Okay, yeah. Yeah, let me write this way. Another 1 comparison. Okay, then we accumulate all the number of comparisons. So x to the 4th times x to the 4th, another comparisons. Okay. So you can see 3 multiplications, or not comparison, the multiplications. Okay, yeah. That's the technique, so you can see. Yeah. So you can get it much faster. Faster? Yeah. Right, yeah. Because here, monomial, we do not consider the coefficient number. Horner's rule, because we consider the general coefficient number. Okay. Other than that, if we use our old way, we need to use 7 comparison, not multiplications for this case. For that case, 3 multiplications, old way, and this way, 7 multiplications, old way. So you can see the save is big. The save is huge. Okay. All right. Then this time for k equals power of 2. And how about that? Power of 2. Okay. Can you find the rule from the first 2 examples? Now we use repeated squaring. Okay. When k equals 2 to the nth power, how many comparisons you need? N, right? Same number, same exponent number. Okay. And multiplications. But if we use the old way, okay? If you do not use repeated squaring technique, if you use the old way, right? Yeah. How many comparisons you need to use? Right. 2 to the n minus 1. Is the difference huge? N versus 2 to the n minus 1. Huge, right? The difference. Now, can you answer question number 10 of the quiz? 1. Yeah, easy, right? Yeah. After this example, you know, it's easy. Yeah. All right. Yeah. And let me see how much time. Yeah. I think you from my clock here, still 5 minutes, right? Yeah. So I want to give you another interesting example. Yeah, interesting example. Probably you can get more points, yeah, in some future assignments. Yeah. This one also some smart way to reduce the now. Our goal, reduce the number of multiplications, right? So use smart way to reduce number of multiplication. Here, I give you another interesting example, okay? This time, I give you a polynomial like this. P of x equals 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. This polynomial, okay, also special polynomial. Now we want to use the minimum number of multiplications to find the value of this polynomial. What's the best way? By Horner's rule, first, by Horner's rule, how many multiplications? Can you tell me? 4. 4, yeah. Although if you use the formula 4, but the leading coefficient is 1. Look at here. The leading coefficient is 1. In the Horner's rule, the last multiplication, we apply leading coefficient with x, right? So here, the leading coefficient is 1, then you can say the last multiplication. So by Horner's rule, you need 3 multiplications. Yeah. If the leading coefficient is not 1, then 4. If the leading coefficient is 1, then 3, because you save 1. Okay, that's Horner's rule. But the question here is, can we do better than 3? Can we do better than 3? Is it possible to do better than 3 number of comparisons? Okay, all right, here. Anybody know when you look at the coefficients pattern here, 1, 4, 6, 4, 1, do you know how special these coefficients are? How special they are? They are not ordinary coefficients. They are special coefficients. Have you seen this kind of thing before? This kind of thing before? Here, let me give you the name so you can do the web search. Okay. Here, these numbers related to a term called Pascal's triangle. Pascal's triangle. Okay. Have you heard of that, Pascal's triangle? Yeah. All right. So we start triangle top 1. That corresponds to 1 plus x to the 0's power 1. Okay. All right. Triangle. Then 1, 1. This corresponds to 1 plus x, the first power. Yeah, because 1, 1 coefficient. All right. 1, 2, 1. That corresponds to 1 plus x squared coefficient. 1, 2, 1. Okay. 1, 3, 3, 1. The number 3 equals 1 plus 2. on its shoulder, two numbers adding together on its shoulders. That's 1 plus x to the fourth, a cube. Yeah. Then 1, 4, 6, 4, 1. Yeah. Also, you get a number from sum of two shoulder numbers. That corresponds to 1 plus x to the fourth. That's the Pascal's triangle. Okay? If you use this Pascal's triangle, you can write this polynomial as 1 plus x to the fourth. Now, 1 plus x, we do not count addition. We only count multiplication. Yeah. This time, how many multiplications you need? Yeah, we just did it. Repeated squaring, this one, we need 2 multiplications, not 3. Much better, yeah. So you can see, if we consider some special structure here, Pascal's triangle, that special structure, then you can reduce number of multiplications. Think about that. All right, so that's it. Yeah, that's